Let's say you are doing a survey of software engineers' salaries, not for any census but just to find out how shitty your pay is. You want to know if you are in the bottom half or the top half of the salaries. As the survey progresses and more data is available, the value of the median salary will change. Being the awkward and anxious and broken thing you are, we all know you want to check after every new data point whether you are above or below median. But you are also lazy, you won't calculate the new median after every new data point manually. That's where you decide to put the only thing you have, your coding skills, to use. Let's look at the possible solutions for this problem. A simple solution would be to maintain a sorted list of all the numbers that we have found so far to be able to find the median easily. When a new number needs to be added to the list of salaries, we'll have to put it in its right place in the sorted list. As you can guess, the time complexity to find the median will be O(1) if you are using an array, and O(n) if you are using a linked list. Similarly, the time complexity of adding a number to the list will be O(n), in both cases whether you are using an array or a linked list. In case of an array, you could use binary search to find the correct position for the new number in O log n, but you will have to shift the numbers after the insertion position. Let's look at a better solution using heaps. We can use two heaps to optimize the accommodate new streaming number in the current data in O log n time complexity, and we can find the median in O(1). Here's how we can do it. We will maintain two heaps, a max heap and a min heap. The numbers we have till now will be split in two subsets, such that, if we sort them, the smaller half of numbers will be maintained in max heap and the greater half of the numbers will be maintained in min heap. We will maintain these two heaps such that the size of the two heaps won't differ by more than 1. Hence, if the size of both heaps is same, that means we have even number of elements at the moment, and their median will be the mean of the root elements of both heaps. If the size of the heaps differ, then the root of the heap with greater number of elements is the median. To see as to why this is the case, observe that since the max heap contains smaller half of the numbers, that means the root element of this heap will be the number in the middle of the sorted list. Similarly, since the min heap contains the greater half of the numbers, its root element will be the next number in the sorted list after the root element of the max heap. Thus, if both heaps contain same number of elements, that means the root elements of both heaps are the two middle elements and the median will be the mean of these two. Otherwise, if one heap is larger than the other, that heap will contain the center element of the sorted list and it will be the root element of that heap. To add a new incoming number from the stream to our heaps, we will compare the number with root element of the max heap. If the incoming number is smaller, then we will insert this element in the max heap. Otherwise, we will insert it into min heap. After insertion, we will check the difference of the sizes of the two heaps. If it's greater than 1, then we will pop one element from the larger heap and insert it into the other one. This way the size difference of two heaps will never be greater than 1. Let's take a look at the code solution. We will define a solution class in which we define two lists, smaller_pq for the max heap containing smaller half of the current set of elements, and greater_pq for the min heap containing greater half of the elements. We will expose addNumber method which will insert the incoming number in one of our two heaps. This method compares the incoming element to the root element of the max heap maintained in smaller_pq to decide that to which heap should the element go. After pushing the element to the appropriate heap, we balance the size of the two heaps, if required. This method uses the private method, pushToHeap to push the element into a heap, and another private method balanceHeaps to balance the size of the heaps, so that the difference in size of the heaps is not greater than 1. The findMedian method will be used to get the current median of the elements encountered so far. If total number of elements we have is even, the median will be the mean of the root elements of the two heaps. Otherwise, it will be the root element of the heap with larger size. The link to the full code with all the private and helper methods used is in the description. Let me know in the comments if you would like me to dive deeper in the code next time, to give a line-by-line explanation. Man, my salary is like a magician's income, it disappears right after I get it.